This video is sponsored by Warby Parker. More on them later. In February 2017, the world watched as the main spillway on one of the largest dams in the world suffered a catastrophic failure, prompting a series of events that led to the evacuation of nearly 200,000 people downstream and hundreds of millions of dollars of damage to critical water infrastructure. I made a video about the failure of the Oroville Dam spillway in California after the independent forensic team released their conclusions about why the structure failed, summarizing their 600-page report. There wasn't enough time in that first video to cover the monumental project of rebuilding both the primary and emergency spillways after the event was over. I got flooded with requests to cover the repairs, and I love a good construction project as much as anyone else. So how do you rebuild one of the biggest spillways in the world after a catastrophic failure, knowing that the next winter flood season is right around the corner? The answer might surprise you. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about rebuilding the Oroville Dam spillways. Oroville Dam in Northern California is the tallest dam in the United States. It was built in the 1960s, creating one of California's keystone reservoirs to smooth out the tremendous variability in rain and snowfall from their climate of hot, dry summers and flood-prone winters. The dam itself is a massive earthen embankment. To the northwest is the main spillway, also known as the Flood Control Outlet, or FCO spillway. At the top are radial gates to control the flow. They release water into the enormous concrete chute before it passes through gigantic dentates that disperse the flow as it crashes into the Feather River below. It's nearly impossible to convey the scale of this structure, which could fit 8 American football fields with room to spare or more than 150 tennis courts. Beyond is the emergency spillway, a concrete weir set a foot above the maximum operating level to provide a backup path for water to leave the reservoir during extreme flood events. If you want more detail about the failure, I encourage you to go back and watch that video after this. I do want to summarize the damages here because you can't really grasp the magnitude of the reconstruction project without an appreciation for how profoundly ruined this event left the spillways of Oroville Dam. Just about all but the upper section of the main spillway chute was wholly destroyed. The flows that broke free from the chute scoured the hillside around and below the structure, washing away concrete and eroding an enormous chasm as deep as 100 feet or 30 meters in some places. At the emergency spillway, overflows had similarly scoured the hillside, creating erosional headcuts that traveled upstream, threatening the safety and stability of the structure and ultimately leading to the downstream evacuation. In total, more than 1 million cubic meters of soil and rock were stripped away, much of which was deposited into the Feather River below the dam. Both spillways were rendered totally incapable of safely discharging future flood flows from Lake Oroville. Even before the event was over, the California Department of Water Resources, or DWR, was planning for the next flood season, which was right around the corner. Having the tallest dam in the United States sitting crippled and unable to pass flood flows safely with the rainy season only 6 months away just wasn't an option. As soon as the extent of the situation was revealed, DWR began assembling a team and plotting the course for recovery. Rather than try to handle all the work internally, DWR contracted with a wide range of consultants from engineering firms across the country and partnered with federal agencies, namely the Corps of Engineers and Bureau of Reclamation, who both have significant knowledge and experience with major water resources projects. In March, less than a month after the incident started and well before it was close to over, DWR held an all-day workshop with the design and management teams to collaborate on alternatives for restoring the dam spillway, focusing on the main spillway. They were facing some significant challenges. With the next flood season quickly approaching, they had limited time for design, regulatory reviews, and construction. Steps that would typically take months or years needed to be compressed into weeks. On top of that, they were still in the midst of the spillway failure, without a complete understanding of what had gone wrong, making it difficult to propose solutions that would avoid a similar catastrophe in the future. Although they had a laundry list of ideas, most fell into 3 categories, nicknamed by the design team as use the hole, bridge the hole, or fill the hole. Use the hole alternatives involve taking advantage of the scour hole and channels carved by the uncontrolled flows from the spillway. If they could protect the soil and rock from further erosion, these new landscape features could serve as the new path for water exiting the reservoir, eliminating the need for a replacement to the massive and expensive concrete chute. The engineering team built a scale model of the spillway at Utah State University as a design tool for providing hydraulic information. They constructed an alternative with a modified scour hole to see how it would perform when subjected to significant releases from the spillway. Sadly, the model showed enormous standing waves under peak flows, so this alternative was discarded as infeasible. Bridge the hole alternatives involve constructing the spillway chute above grade. In other words, instead of placing the structure on the damaged soil and rock foundation, they could span the eroded valleys using aqueduct-style bridges. However, given the complexity of engineering such a unique spillway, the design team also ruled this option out. The time it would take for structural design just wouldn't leave enough time for construction. Fill the hole alternatives centered around replacing the eroded foundation material and returning the main spillway to its original configuration. There were a lot of advantages to this approach. It had the least amount of risk and the fewest unknowns about hydraulic performance, which had been proven through more than 50 years of service. This option also provided a place to reuse the scoured rock that had washed into the Feather River. Next, it had the lowest environmental impacts because no new areas of the site would be permanently impacted. And finally, it was straightforward construction, not anything too complicated, giving the design team confidence that contractors could accomplish the work within the available time frame. Once a solution had been selected, the design team started developing the plans and specifications for construction. Over 100 engineers, geologists, and other professionals were involved in designing repairs to the two spillways, many working 12-plus hour days, 6 to 7 days a week, on site in portable trailers near the emergency spillway. Because many of the problems with the original spillways resulted from the poor conditions of underlying soil and rock, the design phase included an extensive geotechnical investigation of the site. At its peak, there were 10 drill rigs taking borings of the foundation materials. The samples were tested in laboratories to support the engineering of the spillway replacements. The design team elected to fill the scoured holes with roller compacted concrete, a unique blend of the same essential ingredients of conventional concrete, but with a lot less water. Instead of flowing into forms, roller compacted concrete, or RCC, is placed using paving equipment and compacted into place with vibratory rollers. The benefit of RCC was that it could be made on site using materials mined near the dam and those recovered from the Feather River. It also cures quickly, reaching its full strength faster and with less heat buildup, allowing crews to place massive amounts of it on an aggressive schedule without worrying about it cracking apart from thermal effects. RCC is really the hero of this entire project. The design engineers worked hard to develop a mix that was as inexpensive as possible, using the rock and aggregates available on the site, while still being strong enough to carry the weight of the new spillway. In the interest of time, California DWR brought on a contractor early to start building access roads and staging areas for the main construction project. They also began stabilizing the steep slopes created by the erosion to make the site safer for the construction crews that would follow. The main construction project was bid at the end of March with plans only 30% complete. This allowed the contractors to get started early to mobilize the enormous quantity of equipment, materials, and workers required for this massive undertaking. Having a contractor on the project early also allowed the design team to collaborate with the construction team, making it easier to assess the impact of design changes on the project's costs and schedule. Because the original spillway failed catastrophically, DWR knew that the entire main spillway would need to be rebuilt to modern standards. However, they didn't have the time to do the whole thing before the upcoming flood season. DWR had developed an operations plan for Lake Oroville to keep the reservoir low and minimize the chance of spillway flows while the facilities were out of service for construction. But they couldn't just empty the lake entirely. They still had to balance the purposes of the reservoir, including flood protection, hydropower generation, environmental flows, and the rights of water users downstream. The winter flood season was approaching rapidly, and there was still a possibility of a flood filling the reservoir and requiring releases. DWR needed a spillway that could function before November 2017, a little more than 6 months from when the contractor was hired, even if it couldn't function at its total original capacity. In collaboration with the contractor, the design team decided to break up the repair project into 2 phases. Phase 1 would rush to get an operational spillway in place before the 2017-2018 winter flood season. The remaining work to complete the spillway would be finished ahead of the following flood season at the end of 2018. In addition to the repairs at the main spillway, engineers also designed remediations to the emergency spillway, including a buttress to the existing concrete weir, an RCC apron to protect the vulnerable hillside soils, and a cutoff wall to keep erosion from progressing upstream. To speed up regulatory approval, which can often take months under normal conditions, the California Division of Safety of Dams and the Federal Energy Regulatory Commission both dedicated full-time staff to review designs as they were produced, working in the same trailers as the engineers. The project also required an independent board of consultants to review designs and provide feedback to the teams. This group of experts met regularly throughout design and construction, and their memos are available online for anyone to peruse. Phase 1 of construction began as the damaged spillway continued to pass water to lower the reservoir throughout the month of May. The contractor started blasting and excavating the slopes around the site to stabilize them and provide access to more crews and equipment. At the same time, an army of excavators began to remove the soil and rock that was scoured from the hillside and deposited into the Feather River. The spillway gates were finally closed for the season at the end of May, allowing equipment to mobilize to all areas of the site. They quickly began demolition of the remaining concrete spillway. Blasting also continued to stabilize the slopes by reducing their steepness in preparation for RCC placement and break up the existing concrete to be hauled away or reused as aggregate. By June, all the old concrete had been removed, and crews were working to clean the foundation materials of loose rock and soil. The contractor worked to ensure that the foundation was perfectly clean of loose soil and dust that could reduce the strength of the bond between concrete and rock. In July and August, crews made progress on the upper and lower sections of the spillway that hadn't been significantly undermined. Because they didn't have to fill in a gigantic scour hole in this area, crews could use conventional concrete to level and smooth the foundation, ensuring that the new structural spillway slab would be a consistent thickness across its entire width and length. Of course, I have to point out that the chute was not simply being replaced in kind. Deficiencies in the original design were a significant part of why the spillway failed in the first place. The new design of the structural concrete included an increase in the thickness of the slab, more steel reinforcement with an epoxy coating to protect against corrosion, flexible water stops at the joints in the concrete to prevent water from flowing through the gaps, steel anchors drilled deep into the bedrock to hold the slabs tightly against their foundation, and an extensive drainage system. These drains are intended to relieve water pressure from underneath the structure and filter any water seeping below the slab so it can't wash away soil and undermine the structure. As the new reinforced concrete slabs and training walls were going up on the lower section of the chute, RCC was being placed in lifts into the scour hole at the center of the chute. This central scour hole was the most time-sensitive part of the project because there was just so much volume to replace. Instead of filling the scour hole and building the new spillway slabs and walls on top during Phase 1, the designers elected to use the RCC as a temporary stand-in for the central portion of the chute during the upcoming flood season. The designs called for the RCC to be placed up to the level of the spillway chute with formed walls, not quite tall enough for the total original capacity, but enough to manage a major flood if one were to occur. By September, crews had truly hit their stride, producing and placing colossal amounts of concrete each day, slowly reconnecting the upper and lower sections of the chute across the chasm of eroded rock. Reinforced concrete slabs and walls continued to go up on both the upper and lower sections of the chute. With only a month before the critical deadline of November 1st, the contractor worked around the clock to produce and place both conventional and roller compacted concrete across the project site. By the end of the day on November 1st, Phase 1 of the massive reconstruction was completed on schedule and without a single injury. The spillway was ready to handle releases for the winter flood season if needed. Luckily it wasn't, and the work didn't stop at Oroville Dam. Phase 2 began immediately with the contractor starting to work on parts of the project that wouldn't compromise the dam's ability to release flows during the flood season. That mainly involved a focus on the emergency spillway. Crews first rebuilt a part of the original concrete weir, making it stronger and more capable of withstanding hydraulic forces. They also installed a secant pile cutoff wall in the hillside well below the spillway. A secant pile wall involves drilling overlapping concrete piers deep into the bedrock. The purpose of the cutoff wall was to prevent erosion from traveling upstream and threatening the spillway structure. A concrete cap was added to the secant piles to tie them all together at the surface. Finally, roller compacted concrete was placed between the secant wall and the spillway to serve as a splash pad, protecting the vulnerable hillside from erosion if the emergency spillway were ever to be used in the future. Once the flood season was over in May, DWR gave the contractor the go-ahead to start work back on the main spillway. There were two main parts of the project remaining. First, they needed to completely remove and replace the uppermost section of the chute and training walls. Except for the dentates at the downstream end, this was the only section of the original chute remaining after Phase 1. At the RCC section of the spillway, crews first removed the temporary training walls that were installed to allow the spillway to function at reduced capacity during the prior flood season. They never even got to see a single drop of water, but at least the material was reused in batches of concrete for the final structure. Next, the contractor milled the top layer of RCC to make room for the structural concrete slab. They trenched drains across the RCC to match the rest of the spillway, and finally, they built the structural concrete slabs and walls to complete the structure. All this work continued through the summer and fall of 2018. On November 1st, construction hit a key milestone of having all the main spillway concrete placed ahead of the winter flood season. Although cleanup and backfill work would continue for the next several months, the spillway was substantially complete and ready to handle releases if it was needed. It's a good thing too, because a few months later, it was. Crews continued cleaning up the site, working on the emergency spillway, and demobilizing equipment throughout the 2018-2019 flood season. In April 2019, heavy rain and snowfall filled Lake Oroville into the flood control zone, necessitating the opening of the spillway gates. For the first time since reconstruction, barely 2 years after this whole mess got started, the new spillway was tested, and it performed beautifully. I'm sure it was a tremendous relief and true joy for all the engineers, project managers, construction workers, and the public to see that one of the most important reservoirs in the state was back in service. As of this writing, Oroville is just coming up from historically low levels resulting from a multi-year drought in California. It just goes to show the importance of engineering major water reservoirs like Oroville to smooth out the tremendous variability in rain and snowfall. It's easy to celebrate such an incredible engineering achievement of designing and constructing one of the largest spillway repair projects in the world without remembering what necessitated the project in the first place. The systemic failure of the dam owner and its regulators to recognize and address the structure's inherent flaws came at a tremendous cost, both to those whose lives were put at risk and evacuated from their homes, and to the taxpayers and ratepayers who will ultimately foot the more than $1 billion spent on these repairs. Dam owners and regulators across the world have hopefully learned a hard lesson from Oroville, thanks in large part to those who shared their knowledge and experience of the event. I'd like to give them a shout out here because this video wouldn't have been possible without them. California DWR's commitment to transparency means we have tons of footage from the event and reconstruction, much more than I was able to share here. Engineers and project managers involved in the emergency and reconstruction shared their experiences in professional journals. Finally, my fellow YouTuber Juan Brown provided detailed and award-winning coverage of the project as a citizen journalist on his channel Blanco Lirio, including regular overflights of Oroville Dam in his mighty Luscombe. Go check out his playlist after this if you want to learn more. As I always say, this video is only a summary, and it doesn't include nearly the level of detail that Juan put into his reporting. Finally, I want to say thanks to the sponsor of today's video, without whom I could not see faraway objects clearly, nor could I maintain this air of confidence and charisma. Warby Parker is all things vision care, including stores that offer eye exams, but I've been using them for my glasses for many years now. Let me show you how it works. You choose 5 pairs of glasses from their website to try at home for free for 5 days. I love this option because there's less pressure to make a decision than at an optometrist's office, and I can get feedback from my wife. I always pick at least one pair I know I'll like.
Those ones look the best on you.
And one pair that isn't my normal style. Once you've tried them on, pack them up and send them back with a prepaid label. There's no obligation to buy, but glasses start at only $95 with prescription lenses, and you can use FSA or HSA dollars too. It's such a fresh take on purchasing eyeglasses, and I really enjoy the process. If you're a fellow glasses wearer, try 5 pairs of glasses at home completely free at warbyparker.com/practicalengineering.
Can I try those on?
Yeah.
Let me see.
Supporting our sponsors helps support the channel. That's warbyparker.com/practicalengineering. Thanks, Warby Parker, and thank you for watching. Let me know what you think.